Okay, so next speaker is Dr. Hugo Camargo from GIST, and he's going to talk about Q-curvature and path integral complexity.
Okay, thank you, Kunyong, and thank you to the organizers for allowing me to present this work at this amazing workshop. And today, in 30 minutes or less, I want to tell you the very broad idea of a paper that came out earlier this year in collaboration with Pavel Zaputa from the University of Warsaw and Pratik Nandi, who is a student from the Indian Institute of Science, who will be moving to YITP later this year. And our work has to do with Q-curvature and path integral complexity. So as we have been discussing in this interesting workshop, the ADS-CFT correspondence is a very powerful framework which allows us to peer into the quantum nature of gravity. And perhaps one of the most surprising aspects of this duality is that somehow quantum states in holographic CFTs are dual to geometries in asymptotically ADS spacetimes. And as we have also heard throughout this workshop, we still do not have a very deep understanding of the mechanism behind this amazing duality. Now, over the past 20 plus years, we have developed different ideas to try to understand this mechanism better. And one approach, which will be the one that I will focus on today, has to do with looking at gravity from the lens of quantum information science. And in this regard, perhaps one of the most well-known quantities that has taken a central stage is entanglement. And entanglement, as you are maybe aware, has led to a wide variety of results in this context over the past years, even allowing us to resolve some aspects of the quantum information black hole paradox. And what is interesting about entanglement is that, of course, there is a well-known notion of entanglement entropy arising in CFTs from the Von-Neumann entropy. And at the same time, due to the Ryu-Takayanagi formula and the generalizations, we have a very well-known prescription from the gravity perspective. Now, there is another notion which was proposed a few years ago to allow us to peer into the interior of the black holes, which is known as complexity. And this is a notion that appeared in a series of papers by Susskind and collaborators. Now, complexity is a notion that appears in quantum information science, and it has a very precise interpretation in terms of circuits and unitaries. However, it is not entirely clear how this notion should be extended to field theories. At the same time, from the holographic perspective, there seems to be a wide variety of quantities that we can compute that somehow have properties that we expect from these complexity notions in quantum circuits. From the perspective of field theories in general, we can think of complexity as arising as some minimization procedure applied to some cost that we ascribe to, for example, preparing a state or constructing some operator. Now, in this talk, I will focus precisely on this question of how can we obtain some ADS geometries from information containing quantum states. And in particular, I will focus on this aspect here, on the notion of complexity from conformal field theories. H means holographic, and A means asymptotically. Okay, so here is an outline of my talk. I will first describe very broadly and without too many details the idea of path integral optimization and path integral complexity. I will then move to the bulk of the work that we released earlier this year, which is an interpretation in terms of what's called Branson's Q-curvature and the GJMS operators. And I will formulate then the notion of path integral optimization as some geometric uniformization problem. Then, if time permits, I will also discuss some holographic path integral optimization in view of this uniformization procedure. And then I will end with some summary and some future directions. Okay, so path integral optimization. This program originates from the idea of trying to formalize the intuition that somehow hyperbolic geometries should arise from quantum states in holographic CFTs. Now, the original idea of path integral optimization came about in a series of papers in 2017 by the group in Kyoto. And the idea was that we take some information that is well known in the tensor network community. So tensor networks are very efficient methods that allow us to compute quantum states. And in particular, they allow us to capture the entanglement structure of quantum states, which is very important in ADS-CFT. So it turns out that the entanglement structure of quantum states in critical theories, for example, in CFTs, can be efficiently represented by some tensor networks, which resemble hyperbolic slices. And the clearest example of this case is MERA. MERA is a tensor network, which means multi-scale entanglement renormalization ansatz. And in a series of papers, the idea was being more or less formulated with that we should be able to somehow understand how hyperbolic slices arise from information in quantum states. And path integral optimization is the formalization of these ideas in a concrete way. So the idea is to start, for example, with some CFT defined in some d-dimensional space, and we consider some state being prepared by a Euclidean path integral. Now, for my talk, I will focus on discussing vacuum states, but similar ideas can be done for example, thermal states or some primary states in CFTs. But the idea is the following. Suppose that we have some state represented by this path integral, and we want to represent this state with some tensor network. Now, we don't know exactly how to prepare this state, and this state lives in some geometry. So I'm starting with this picture on the left, and I think, well, I'm going to prepare this state in some lattice, for example, which is some uniform lattice with some lattice spacing epsilon. Now, in tensor networks, it's usual that not every tensor that we used initially is necessary for actually capturing the entanglement structure of the state. So one should remove some unnecessary sites from this computation in such a way that we don't change the state, but we keep the important entanglement information. And the idea is that we deform this metric on which we discretize our state, and somehow through these tensor networks optimization algorithms, we achieve something that resembles some hyperbolic geometry and which should correspond to some tensor network in the MERA. So in this sense, what we're doing is we're optimizing the way in which we prepare the state via the geometry on which we are representing it. So optimizing the state means removing unnecessary sites from this tensor network, leading to some tensor network which has some hyperbolic geometry. Now, I know that this may sound very abstract, but fortunately, in 2D CFTs, there is a very precise way in which we can visualize how this works. So suppose, for example, that we start with some preparing our state in some generic metric, and we consider some Weyl rescaling that deforms the metric. Now, it is well known that under this Weyl rescaling of the geometry, the measure of the path integral changes in this way. This was observed already in the works by Polyakov in 1981. It has to do with how, for example, the Jacobian changes under this sort of transformation, and using some heat kernel computations, one can arrive at this result. And it turns out that the proportionality factor between these two integration measures is the well-known Liouville action. And in this Liouville action, we have the central charge, and we also have some cosmological constant, which I will explain later what it means. And the idea is then that because the measure of the path integral changes in this very well-known way, we can actually know how this wave functional changes under this Weyl rescaling. And the idea is that if we are able to optimize the way that this wave functional changes, we can have the optimal geometry on which we can prepare the state. So in some sense, the exponent here, this functional, will allow us to, will tell us the cost of preparing the state in this particular way. And we can think that the minimization of this cost will give us a notion of complexity of preparing this state. And some important comment is that this notion of path integral complexity measures is a measure of relative complexity between different geometries. So in this sense, optimizing the path integral is equivalent to minimizing the path integral complexity. Now, once we extremize this action, we arrive also at the well-known Liouville equation, which takes this form. Notice, for example, that this Liouville equation is basically telling us that we should find geometries where the Ricci scalar is constant and equal to the cosmological constant. Notice as well that the trace of the stress energy tensor is given precisely by this Ricci scalar. And for example, if we want to solve this equation, we can start, for example, from some flat metric in some local coordinates. And if we impose a boundary condition, which is related to the way that we prepared the state originally, then we obtain a hyperbolic metric, which is precisely according to this idea that we should somehow obtain hyperbolic geometries from states in at least in 2D CFTs. In this case, this epsilon is a UV cutoff in the theory, or the lattice spacing in the tensor network. And this mu, which is this mu appearing here, you can think of it in some way as controlling the amount of optimization. It measures more or less the area of, we should think of how many sites per unit area in the tensor network there are. And a fully optimized metric corresponds to setting the cosmological constant mu equals 1, but in general, you can think of having different measures of how optimized this tensor network is. And precisely, if we evaluate this cost function on this optimal geometry, we obtain a measure of the optimal path integral complexity. And this turns out to be somehow proportional to the volume weighted by some UV cutoff. And what was interesting at the beginning, at least in 2017, is that this gave some nice corroboration with these ideas of complexity equals volume. And the lesson from this is that it is less costly to prepare a state in a hyperbolic geometry than on a flat one. Now, of course, the question then arises, is it possible to actually make some similar computations in higher dimensional CFTs? In other words, what would be the higher dimensional analog of this cost functional? Essentially, what we're asking is, how do partition functions in higher dimensional CFTs change under similar transformations? This is a very complicated question, and this actually leads to the so-called anomaly actions in higher dimensional CFTs. And perhaps the first example is called the Rigert action, which is a local action in four-dimensional CFTs, which somehow captures partial information about this transformation of the partition functions. So this is, in general, very complicated. So in order to make modest progress on this question, we want to make the following assumptions. We first consider only vial rescalings of the metric. This constrains the type of conformal transformation that we consider. And at the same time, we will focus only on even dimensional manifolds. Now, the first assumption actually allows us to focus on a family of operators and curvature scalars, which are conformally covariant. And the operators are called Gram, Jean, Mason, Sparling operators. By the way, this Gram here is the same Gram from the Pfefferman-Gram coordinates in ADS. And also to this Branson's Q-curvature. And the second assumption actually helps us to make the field theory local. And there are some very interesting papers on this matter. So very generally, very generally, what are these things? So in general, there exists a family of differential operators and curvature scalars, which satisfy the following transformation rule under a vial rescaling. You can think of this equation diamond here as somehow a generalization of the usual transformation law for the Ricci scalar when you do a vial rescaling. So it turns out that these kinds of objects, which are much more general than the Ricci scalar, satisfy this very nice transformation property. And in general, these objects, one can construct them. There is a very precise way of constructing them for any dimension. But here I'm only showing the leading order structure of these objects. So this PD will behave as some Laplacian to some power d/2 plus some lower order differential operators. And this Q curvature D will behave as applying the Laplacian to some power to the Ricci scalar plus some higher curvature corrections. So actually, in 2 dimensions, this GJMS operator is nothing else than the Laplace-Beltrami operator. And the 2-dimensional Q curvature is nothing else than the Ricci scalar. But in higher dimensions, these objects become much more complicated and involve higher derivatives and higher curvature terms for the Q curvature. Some of you may be familiar with the Yamabe and Pannates operators. And these objects are generalizations of these operators in higher dimensions.
So I still don't see what
So the point of the transformation is that we're asking how these objects transform under a Weyl rescaling, because basically we want to do the same trick that we did in 2 dimensions, where we consider some rescaling of our geometry, and then we want to optimize the geometry. And it turns out that because these operators satisfy this nice transformation rule, we will be able to formalize the same procedure in higher dimensions. This may be clear once I show you this part, which is the following. If we, for example, fix the Q curvature of the Weyl rescaled metric to be a negative constant, then this equation here can actually be thought of as the Euler Lagrange equation from the Q curvature action, which is some higher dimensional analog of the Liouville equation. This Q curvature action is usually referred to as the generalization of the Liouville action in higher dimensions.
So what I'm asking is maybe this can be transformation rule of Q, and you don't have the transformation rule for P. So
they transform in this way precisely. So it's one transformation rule for both objects. So far, yes, but the only constraint is that we are only considering Weyl rescalings of the metric, and the beauty is that this transformation rule works for any G hat that you put. The only thing that's important is how this G hat changes under the Weyl rescaling. That's the only thing that I'm saying. Is it clear? Is it clear?
no, I still don't get it,
Okay.
because you cannot use just one relation to define the you define the transformation property of the P and Q both.
So okay, they do have some. So I'm showing here basically the transformation rule that will allow me to show you that this comes from like from an action. The actual transformation laws may be a bit more involved, and actually what I'm showing you here is actually what's called the critical Q curvature and the critical GJMS operators. In general, these are, you can define a wide variety of objects in different dimensions and including 2nd order, 3rd order, 4th order derivatives. But these ones are called critical because this gives a d-th order differential equation for a d-th dimensional spacetime.
Maybe what I can do is maybe I understand that this one as a transformation of the Q, and the P is just the residual part which appears
right
in the Q.
I think it's useful to think of it in this way. I agree.
Okay.
So it can actually be shown that this general Q curvature action satisfies some similar properties to the Liouville action in 2 dimensions. In particular, if we remove the volume term, which is this one here, from the action, this satisfies similar co-cycle conditions, which are useful in the community of quantum information when we try to find measures of relative complexity. Now, this leads me to discussing the so-called geometric uniformization problem. And the question is the following. Given an arbitrary reference metric G hat, is it possible to find a conformally equivalent metric that is a metric that I obtained by some Weyl rescaling with a constant negative Q curvature? And because of what I showed you in the previous slide, the answer is yes. And this problem is usually referred to as the geometric uniformization problem. If you think about it in 2 dimensions, this solution is actually trying to formalize how the different types of geometries that we can have. For example, we can have a positive scalar curvature, a 0 scalar curvature, or negative scalar curvature. And this is, in some sense, the higher dimensional analog of this question. It is obviously just a partial answer to the whole problem of geometrizing or uniformizing geometries in higher dimensions, but it is the let's say it is the correct answer in some sense if we only restrict ourselves to Weyl rescalings. So to make contact with the discussion in 2-dimensional CFTs, if we start, for example, from a flat metric in some local coordinates, the equations of motion that I showed you before, which is this transformation rule when I impose the condition that the transformed Q curvature is constant, this becomes this equation, which is a d-th order differential equation for phi, where this lambda is a constant and is the cosmological constant. And if we impose similar conditions to the 2-dimensional case, we actually find that the solution is the same in some sense. We find a negative constant Q curvature geometry. This geometry will also have constant Ricci scalar, but what is important is that this one has constant Q curvature. So, and in this case, this mu here, which I defined here as some transformation of this cosmological constant, also works as some degree of optimization, which fixes the value of the Q curvature. And in this sense, the usual path integral optimization procedure in 2D, we can recast as a geometric uniformization problem in higher dimensions. And if we evaluate this Q curvature action in this type of geometries, we get a similar scaling to this complexity equals volume proposal. Okay, now I will change gears a little bit, and I will discuss the holographic procedure, which is thought to be analogous to this path integral optimization procedure. Now, in a series of recent papers last year, the group in Warsaw, which was led by Paweł Zaputa, they asked the question of what would be the analogous procedure to path integral optimization from the bulk perspective. In some sense, yeah, what if we have some states in some holographic CFTs, and we optimize the states and obtain some hyperbolic geometry, what would be the analogous procedure from the ADS perspective? And they noticed that this may be related to the maximization of Hartle-Hawking wave functionals in ADS gravity. Now, before I describe this part here, I will just remind you that initially or typically when one thinks of Hartle-Hawking wave functionals, one thinks of preparing a state on a time slice. It's a functional of the induced metric. And one thinks about the evolution of the state in time using some ADM formalism. And this naturally leads, for example, to the so-called Wheeler-DeWitt equations. I'm not thinking about that. What I want to show you in this case is a different type of idea. I want to construct a state which gives me, let's say, the quantum state that lives in this region M. And I'm taking this state to evolve in some sense from this cutoff surface sigma up to some region B, to a surface B in the bulk. And this is the way that I'm preparing the state. I will fix the metric of the region M to be a slice, to be part of a Poincare patch. And the metric in B, I will impose that it has this very particular form. This is by no means the most general form that the metric can take, but for the sake of comparison, I will impose this condition. And in this wave functional, there are two components in the action. There's the usual Einstein-Hilbert lambda action. There's the Gibbons-Hawking-York. contribution that will have some part in sigma and one part in B. And then I will furthermore add a tension term because I will think of the surface B as a brane. It is not a back-reacting brane. It is just a probe-brane. And you can think about it in some sense like in the ADS-BCFT procedure. And the idea is that if I can somehow optimize this wave functional, by performing some semi-classical evaluation of the action, I will find the optimal geometry of the state. And this is precisely what we do. We evaluate semi-classically this action and we impose the Neumann boundary conditions. And it turns out that we similarly find this type of hyperbolic geometry. This is now the geometry on the brane B. And once again, we can identify some parameter that is associated with the optimization of the geometry, which in this case will be linked to the brane tension T. So if we follow the analogy from the usual path integral optimization procedure, if we set this parameter to 1, this means that we have to invariably set the brane tension to 0, which tells us that now in this case, the brane will be located at the tau equals 0 slice. And this is the way that we optimize, for example, vacuum states in this procedure. Now, if you remember from the Q-curvature action, there were some higher curvature terms that appeared naturally as we went to higher and higher dimensions. But in this picture of holographic path integral optimization, it seemed like there was no need for such a thing. So how do we reconcile these two pictures? In other words, how does this idea fit into the holographic picture? One thing, and perhaps the most naive thing that one can do, is one can think that instead of just having some tension on the brane, we can include some higher curvature terms on the brane in some arbitrary way. And for example, if we focus just for the sake of presentation on the first term, this term, adding this term to the brane and then following the semi-classical evaluation of the path integral, will lead to some modification of the Neumann boundary conditions. But more surprisingly, we are still able to optimize this geometry in in a very similar way, where now this mu parameter will be not only associated with the brane tension, but it will also be associated with alpha, where alpha is this coefficient appearing in the contribution proportional to the Ricci scalar. And if we furthermore impose a fully optimized metric, this gives us a constraint on the alpha, meaning that we can judiciously add higher curvature terms on the brane action and still recover optimized metrics. In the paper, we discuss the addition of more terms, but I just wanted to show you how this idea works. And the point is that this somehow looks like a counter term action, but it's not quite a counter term action. Okay, since I'm running out of time, I just want to give you a brief summary of what I told you today. So in this work, what we did, we proposed this generalization of the usual Euclidean path integral optimization to higher dimensional manifolds. And we used this via the uniformization of geometries, of conformally equivalent geometries. This Q-curvature action, we showed, it's an important part of our paper, that it can be thought of as a genuine relative complexity measure. And one thing that I didn't discuss, but that is also very important, the Q-curvature is actually related to the A-type anomaly in higher dimensional CFTs. It is related to it. And a good discussion of this fact can be found in this paper by Virginia and Diaz. At the same time, I showed you that this idea is also consistent with the perspective of maximizing Hartle-Hawking wave functions. And one thing that we briefly touched upon in our paper is that this procedure of adding some higher curvature corrections may be connected to TT bar deformations by including some counter terms on the brane. One thing that I didn't discuss, but I want to mention, is that in the lore of the quantum information science community, there is the question of penalty factors. And there is a way in which can actually make some comments about fixing penalty factors naturally from the optimized geometry. Some further directions to finish my talk. we would like to understand if we can make some more precise connection to these TT bar deformations. And we would also like to sharpen the discussion of penalty factors and how do we interpret higher curvature terms from the tensor network perspective. This is a very important question. One question that many of you may have at the moment is how can we generalize this approach to general conformal transformations? Because it's important that we somehow go beyond just Weier's rescalings. A question that may also pop in your minds is what happens in odd dimensions? In odd dimensions, these GJMS operators become non-local. So the theory becomes non-local, and it becomes difficult to treat in a similar way as I did today. There are some indications of how this may work. This is this work by Thurston describes some geometrization in three-dimensional manifolds, and there are some further discussions of non-locality and in odd dimensions. How can we reconcile this work with these new proposals of holographic complexity that appear in this complexity equals anything ideas? And finally, is it possible to connect to other insights that have appeared recently on cost functions in holography? And these are some of the open questions that we still have as we finish our paper. And I would like to thank you for your attention.
Okay, let's thank Hugo for an interesting talk. So is there any question?
How do I go back on the slides? Sorry. Yeah. Okay.
Thank you. Your talk. I have a naive question. The meta method always guarantees the hyperbolic structure in geometry, or any other possibility to depending on some boundary condition.
Sorry, I missed the first part of your question. Sorry.
Meta method always guarantees the hyperbolic structure in geometry, or any other possibility depending on some boundary condition.
So this idea that MERA somehow should correspond to a slice of ADS, this was done by Swingle in like the 2005 or something like that. I think we have slowly understood that this connection between MERA and hyperbolic slices is a bit more subtle, because MERA somehow doesn't give us the full information, and in works by Vidal, we actually need to consider modified versions of MERA, which include some other tensors in the network. Invariably, a particular type of geometry that Vidal proposes can indeed be associated directly with hyperbolic slices. MERA itself is not really associated with hyperbolic slices.
Depending on some renormalization scheme
Yes.
used in MERA.
Yes.
Thank you.
Okay, so any other question?
I have a question. From you reviewed this CFT path integral optimization.
Mm-hmm.
So there at finite temperature,
yeah,
you can finite temperature ADS maybe it's the same, but the black hole case, what can you see?
You mean from the holographic or the usual CFT? The usual
holographic CFT, of course.
You can do, for example, you can impose that instead of working with the vacuum state, you have a thermal state.
Yes.
And then the geometry that you will get is BTZ black hole, for example.
But before and after the transition, then what's the difference in? Can you see the transition?
What do you mean by transition? Sorry.
I mean the Hawking case transition.
That's a good question. I'm actually not sure. I'm not sure. I don't want to make any comments on that. I'm not sure. I'm not sure.
Okay, so any final question? Okay, so if not, because we are now running out of time, I think let's close this session. Okay, let's thank Hugo again. Good. So